Hi everyone, welcome to Atelier3D MC Introduction and Tutorial. I'm Mona.
You should do with the microphone because otherwise we don't hear you.
Okay, what about?
Then you should start in front of it.
Okay, sure.
Because if you go away, we don't hear
Okay.
you. All this. That's a possibility.
Thank you. I'm Mona Omidyeganeh. I'm from National Research Council Canada. I've been working on brain imaging for a few years. Here I have two of my colleagues who are the main contributors in A3D. And Louis Borgeat is the first contributor, and he has been working on 3D imaging and processing and visualization R&D. And Philippe Massicotte, who is the main A3D software developer and manager. And I have been working on this project for couple of years with MSIN as research associate, and now I'm working with NRC Group to help develop new features for A3D. Okay. Is it better now? No. It's on. Hello?
There we go.
Okay. Okay. Atelier3D software was first developed to visualize and analyze large 3D images, make it possible to have different layers of the image, and it has had lots of applications, for example, in health, manufacturing, security, heritage, and etc. Here you can see some snapshots of the applications that it has been used before. After the researchers at McGill started to work on BigBrain slices, and they tried to make a 3D atlas from the 2D sections. This software has been developed and upgraded to be able to visualize the intermediate steps of analysis. It makes it possible to see the results of alignment and intensity correction. After that, when the scientists started to work on segmentation of different segments of the brain manually, this software got upgraded to make it possible to validate the works done in other tool sets, for example, MNI display, where the analyzers, they sketch the boundary of 2D sections and then put them together as a stack in BigBrain. After that, they upgraded the A3D to make it possible to manual annotation and surface extraction from these 2D manual painted sections. In this tutorial, first I will go through main features and capabilities of A3D MSIN. Then I talk a little bit about current status and main use cases of this software, and go a little bit in summary about underlying technology. And after that, we will have the software tutorial where I will talk about some main features of A3D and show how to use it. It will be some steps, including the visualization and analysis capability tool, workspace creation and organization. I will talk about how to import and export data in A3D and how to annotate and iteratively create 3D volumes from 2D painted boundaries. And after that, I will show some results and ways how to extract surfaces and analyze them. After this tour, you will be able to reproduce and recreate all these steps by yourself and navigate through this software. And then we will go through the discussion and question section. A3D MScene is a high-resolution visualization and analysis software which make it possible to interactively navigate for all data sizes, including 1 micron. The data can be used locally or remotely, and it provides high-performance data server, and it makes it possible to overlay hundreds of images and sparse voxel annotations and structures and surfaces over the histology. I will show some examples of this later. It provides classical 4-quadrant interface, and one of the important abilities of this software is to provide native or oblique reference frame. The workspace structure in this software makes it possible for the users to interface efficiently and manage the data and organize the work very well. You can annotate hundreds, you can upload hundreds of annotations, outputs, and intermediate steps, and you can go through all of them using tree structure. And it has efficient workspace using XML file format to support the directory structure. The robust voxel-based annotation pipeline in this software make it possible to have triaxial and oblique multi-resolution annotation interface at any scales which has been tested by 1 micron stack. Also, it provides semi-interactive surface and volume extraction at 20 micron, and we are working on making it for 1 micron possible. There are lots of different formats that are compatible with this software: Mink raw data, OpenVDB voxel formats, OpenSeaGraph mesh formats, and MNI objects, SVG, and etc. Also, open source converters can be used to convert different kind of voxels and meshes and make it compatible with this software. This software is in C++, and lots of capabilities are installed with it on the local laptop or device, and installers are available for Windows 10, Ubuntu 18, and 20. And there are lots of documentations integrated in the software that when you navigate through it, it will help you get whatever you want. In this tutorial, we have some files make it available in Google Drive. You can scan this QR code and access to the folder. In this folder, you will have a 3D download link and installation guide. You will have a 3D Windows installer, which you only need to double-click on it and install it. After that, it asks for you to provide the key for that. You should email to me or my colleagues that I will provide you the email address to generate this key for you. It's free, but we want to keep track of who is working with this software. And also, we have multiple explanatory videos in the repository, and you can access this presentation file and link to the BigBrain data and the data samples of the surfaces. Before I start to go through the documentation and show you how to use this software, since I'm going to use the results of the work of other colleagues, I will give credit to them. Dr. Sadiqat and Aisha Altin-Kaya from McGill, Sherry Jones, PJ and Claude from McGill, and also Andrea Brandster, who is from Jülich. And for the visualization, I'm using the cortical layers that Conrad Waxstyle has created. Okay, the first step is how to open the workspace. and do the basic navigation. As you see, you open the A3D and you choose your workspace, which should have A3D extension. Then you can see the BigBrain volume here. With left button, you can navigate through each plane. And with the right click, you can move the brain. You can zoom in and zoom out. And you can press F to have the full screen of each plane or the 3D volume. And you can press F back to go back. Now I will show how to work through 3D volume quadrant. You can choose the planes to be visible or no by toggling them to be invisible or visible here. You can see the surfaces in this 3D space. You can make it transparent or not transparent. Here you have the option to choose how to go through or add the transparency to be able to go through all the different parts of the surfaces. You can see lots of surfaces and 3D meshes all together, or you can choose and toggle them to make them visible or invisible. You can press check here to omit the 3D histology to be able to see the surfaces in much more details. One of the main advantages of this software is it makes it possible for the user to create and set his own oblique reference plane. It's very important because sometimes you're working with a special part of the brain and segment of the brain. You want to show some results or work or draw some parts of the brain, and you want to have this reference plane set to this structure. To do so, you can zoom in and here in the in the left bar, you can choose your reference and name it whatever you want. And then you can paint the reference frame using the virtual tools. You can change it, you can rotate it, you can edit it using these visual tools. You can even determine the values and by yourself. For example, if you have the numbers or the perpendicular vectors, you can set them here by choosing this. So you can choose the center of your new axial environment that you're gonna to use. The other option is it makes it possible to have both reference planes together and help you to navigate through this. You can play here and choose which one you want to have the main reference, and even you can have all of them together. Next, I will talk about how to import meshes and voxel annotations on top of each other and show how it works. To do so, in the workspace, you can open the new task and then open the voxel annotations that you have provided. The extension should be A3D sparse. As you see, I'm showing the cortical layers annotated. Each voxels are annotated with different colors. And you can zoom in, zoom out, and work through them. Also, you can open the mesh on top of this. These are 3D surfaces. And you can go through different 3D surfaces and make them visible, invisible, to see how they look and how they interface together. In the workspace, you can choose the box to omit the 3D voxel or every other mesh or annotation. And also you can omit them grouply or individually. Next step is how to create a point of interest and lines and labels. We can create, first we create a new task, then we choose a point of interest. We can open one or we can choose or new point of interest. We can customize it, we can name it, we can change the name, the color, we can make the name of the annotation visible and invisible on the 3D surface. And we can create lines. The lines are going to be created by connecting two or more points. For example, here we choose 2 points and change their name. And even changing the colors. And then by grouping the point of interest, we can click Create Line. The name of the line is the first and the last point, but it can be renamed, and also the annotations can be displayed or become invisible using these toggles. You can save the color map and open it later. And next, you can create contours, which I will talk about later in the next video. This is the most important part of my presentation, where we try to create 3D volume from 2D contours. To do so, we have chosen the subthalamus nucleus, which is one of Aisha's work. To do so, we want to create annotation and paint 2D boundaries of this structure. It is roughly done to show only as a demo, but it can be done in more details. We zoom in, for example, we are going to paint in coronal surface plane. We choose the contour, and here we choose the name, and we label it. We should always use a point as a reference point that, for example, we are going to paint in different planes. Then we are going to group them and make a 3D surface. So the first step is to paint the boundary of the structure. Then we should label it using this. Usually, you can paint in every slice, but usually scientists and researchers only paint every 10 or 20 slices. To go up and down between the slices, you can use page up and page down for that moves every 10 slice, or minus and addition sign to go one slice up and down. As you see, we are we have the ability to redo or erase if we do some mistake or something like this. And we do the painting for every other slices. Be noted that, for example, when you are going to create a 3D surface, you will mention that you should at least have a painted area, a painted 2D boundary every 20 slice. And if you go upper, for example, if we have a gap more than 20 slice, it will divide your surface in two pieces. Now you should save the contour and the reference point in your project and mapping. Now, to extract the surface, you click right and choose the surface extraction. Here you have lots of options. You mention which directory, which name, which label, and do you want to go any Gaussian filtering to smooth your mesh, and also which you can do the surface extraction using all the paintings or only the paintings with the label, for example, number 75 that we have done on SDN. And also we should mention that the data are painted in which plane. For example, here we have data painted in the coronal plane. And then press start. and the mesh is created. You can see the overlap between the 2D painted and the 3D surface. When you go through it. This is the surface that has been painted. As I told you, this has been done roughly only to show the ability and the demo. But the most important part here is to have closed loops. If you have any gap between the painted labels, you will get an error. And in the error, you have the link to the slice that you have made the mistake. You can easily go there and complete the paint and save it and run it again. And this is where I told you that the difference between the distance between the painted slice shouldn't be more than the predefined slices. For example, here we defined it equal to 20. Here. And when the distance is more than that, it creates two different 3D mesh. Next, what I'm going to do is to use this 3D mesh extracted slices to use it and slice it in different planes. And try to correct that to have a better view of the 3D, better and improved 3D surface. As you remember, we painted in chronal plane. Now, what we are going to show you is to create contours from the 3D surface extracted in different planes. In the sagittal plane. And when we run, we will have the 2D contours extracted from the 3D surface. Okay, here we see that we have some errors. We want to fix it because this error is because of the gap between painted sections. So we can start working on the other plane. Here we go to sagittal plane and erase the errors and fix it manually. Then we extract a new surface using the information of the 2D contours in X plane, in sagittal plane. Okay. You see the new surface here. You can open the previous one and see the difference between these two. at the same time. Here you can see Sherry's work, which she has worked on this surface extraction on hypothalamus, and she has used the same workflow where she has painted in the coronal plane and then created the 3D surface. And next, using the A3D, she calculated the 2D surfaces, 2D boundaries in sagittal plane, and after that, using the A3D, she created the 3D surface. I also want to show some example of how to use it, use A3D in small displays. To do so, it's better to make the workspace as small as possible. And you can move each window and make it only one column. And the appearance of the A3D will be preserved between different sessions. This is the current status of the A3D, and mostly it has been used for 3D surface extraction and creating atlas, brain atlas with high resolution. The next step of this software is to make it possible to view and display 2D 1 micron sections on 3D BigBrain 20 micron space. This is a work that I have done with Claude at McGill, and we are working on releasing this version. As you see here, when you have the 1 micron slices on top of the 20 microns, we will have much more details, and even we can zoom in and see the neurons. The other work that we are working on is, as you saw, and I illustrated before, when the researchers and scientists paint the 2D boundaries of the segments, and we create 3D, we will see lots of jaggies and in the 3D surface. What I have done is working on resampling and add the curvature smoothing on this to create a better looking surface while preserving the accuracy and adding no complexity to the system. For the accuracy, I have tried to preserve the area and volume and distance between the smoothed and reference surface. For example, here, when you saw the surfaces of basal ganglia that Aisha has painted, these are the results of my work that I have smoothed. As we talked, the 3D scene is fully usable for manual annotation and segmentation. And for next steps of developing this software, we are working to release 1 micron section, 2D 1 micron section display on top of 3D BigBrain space, and adding efficient surface smoothing to manually painted surfaces that are worked with the scientists. Also, we are working on better compatibility with other tools and direct mesh and vector contour manipulation and more automation. The opportunities for code sharing, API-based participation, and open sourcing will be discussed too. Now I think you have a good view of what is A3D and what are the applications that you can work with. You can scan this QR code and download A3D and ask for the registration code and get started. Thank you.
Why is the software not open source?
It's open source.
Can I download the source?
Louis, I think you can answer this.
We cannot hear the question.
Okay. He's asking if A3D is open source.
Okay, so we have not put the code online, basically because right now we don't have the bandwidth to manage a large open source project that would be entirely open, but we're happy to share the code and collaborate with anybody who has an interest. So I guess that's a yes and no answer, but the code would be available for people interested, for sure. And a reminder that I cannot hear the people in the crowd.
Sure. Is there any question?
We have microphones for people on the ground, so they can step up.
Okay.
They just come.
If there is no question, I'm thankful for participating in this tutorial, and please send me or any other people in the group for the key, and we will be happy to discuss about more details. Thank you.